If a car engine breaks, you usually know exactly what to do. You just you pop the hood, you look inside, and you find the broken part.
Right, it's right there in front of you.
Yeah, exactly. You replace a spark plug, or you swap out a cracked belt, and the machine just runs again. It's contained. It's predictable.
I mean, if the spark plug fails, the mechanic literally points right at it and says, there's your problem.
Right. It's a very comforting way to look at the world. We love systems that are isolated and binary. It's either broken or it's not.
But then you step back and you try to apply that exact same mechanical logic to the planet we live on.
Oh, yeah. You look at the Earth, and suddenly that neat little engine schematic is completely useless. There is no isolated spark plug here.
No, not at all.
If something breaks in the ocean, it somehow, affects a mountain range 1,000 miles away.
Yeah.
We're looking at a planetary landscape that is just a giant, impossibly tangled web.
It is the absolute definition of a complex, interconnected system. You really can't touch one part without sending ripples through the entire structure.
And that is exactly the puzzle we are unschooling for you today in this deep dive. We have a genuinely fascinating document on the table titled Earth is a System, Energy, Matter, and Life.
It's a great read.
It really is. And instead of just skimming the surface, we are going to tear this thing apart line by line and figure out the actual mechanics of how the world outside your window operates. To make sure we don't miss a single detail, I'm going to read the core text exactly as written, step by step. And we're going to unpack the why and the how behind every single concept.
Because once you understand this stuff, you will never look at a rain cloud or a patch of dirt the same way again.
You really won't. So let's jump right into the deep end. The document opens with a section called Think It Over, and it throws 4 really provocative mysteries at us right out of the gate.
Okay, let's hear them.
So reading exactly from the text, it asks, quote, how does the warming of Arabian seawater affect the southwest monsoon in India?
That's the first one.
Yeah. Then it asks, if a large forest is cleared, how can that affect the flow of a river in that area?
Right.
Then, what might happen to coastal cities in India if glaciers and polar ice keep melting faster? And the final one, how would increasing carbon dioxide levels in the atmosphere affect the ocean plankton?
Those aren't just warm-up questions. Those 4 scenarios are the entire foundation of what we're discussing today.
They really set the stage.
They do. Notice the common thread in every single one of them. They are pairing things that, to the naked eye, seem completely divorced from one another.
Right, like warm water in the Arabian Sea dictating how much rain falls on a landlocked farm.
Exactly. Or chopping down a forest and somehow changing the physical flow of a river miles away. It's all about these invisible connections.
Yeah.
And just to make sure we're completely grounded before we move forward, let's just quickly define 2 terms in those questions.
Good idea.
So, a monsoon isn't just a heavy rainstorm. It's a massive seasonal shift in the prevailing winds of a region. In India, it pulls in moisture from the ocean and delivers the critical rainfall that sustains agriculture for, over 1 billion people.
Wow, okay. And the other term was plankton, right, from the last question.
Yeah, ocean plankton. Plankton are microscopic organisms. Some are tiny plants, some are tiny animals that just drift in the ocean currents.
So they're invisible to us.
Mostly, yeah. But they form the absolute base of the entire marine food web. And as we'll see later, they are basically the lungs of the ocean.
Which leads perfectly into how this document frames the big picture. Let's look at the introduction to Chapter 13. I'll read the premise exactly.
Go for it.
Quote, life on Earth is powered by a constant flow of energy and matter. The sun is the main source of energy. In addition, the Earth's hot interior and chemical reactions in the air, water, and rocks also drive the flow of energy and matter.
Okay, that's the power source.
Right, it continues. During the middle stage in Curiosity, grades 6 to 8, and in earlier chapters of this textbook, you explore these ideas as separate content pieces. For example, you learned how sunlight drives winds and the water cycle, how plants and microbes cycle nutrients, how the Earth's tilt causes seasons, and how human activities are modifying air, water, soil, and climate.
Which is how we usually learn it, right? Isolated.
Exactly. But then it finishes with, in this chapter, we will consider these processes together as belonging to one Earth system made up of interacting spheres.
I just love how they frame that. They are explicitly asking you to stop looking at the world in isolated pieces.
Yeah, no more little separate boxes.
Right. We all learned about the water cycle in elementary school. We all learned about the seasons. But this is asking you to zoom all the way out.
To see the whole machine.
Yes. Imagine the entire planet is a massive factory, and everything in it, every gust of wind, every sprouting seed, every rushing river, runs on a giant battery.
And the text tells us the primary power source charging that battery is the sun, right? Just constantly blasting us with energy from space.
Mostly the sun, yeah. But there's also a secondary internal power source,
Hmm.
the radioactive molten core of the Earth itself, bubbling up heat from below. And then the text introduces this really crucial word, spheres.
Yeah, that word spheres can be a bit confusing. When I hear sphere, I just think of a geometric shape like a globe or a ball.
Right, right. But in this context, think of spheres as the massive interconnected departments of that planetary factory. They are the massive domains of matter that make up the Earth.
Let's actually define those departments because the text gives us 5 specific ones, complete with geographical examples. Let's go through them.
Let's do it.
First, the text says, quote, geosphere, solid rocks, soil, landforms, like the Deccan Plateau and the Thar Desert, and the Earth's interior,
So geo comes from Greek, meaning earth or ground. This is the physical structure.
the solid stuff.
Exactly. It's the dirt in your garden, the massive granite peaks of mountains, the sweeping sands of the Thar Desert, and importantly, all the rock and magma extending thousands of miles beneath our feet down to the core. It's the physical scaffolding.
Next, the text lists the, quote, hydrosphere, liquid water in the form of surface water, such as oceans, rivers, like the Ganga-Brahmaputra river system, lakes, and groundwater.
Hydro simply means water. But note the key word there, liquid.
Oh, okay.
The hydrosphere is every single drop of liquid water on the planet. The vast oceans, the massive rivers like the Ganga-Brahmaputra carving through the landscape, the puddles after a rainstorm, and the immense hidden aquifers of groundwater sloshing around inside the geosphere.
And that distinction about liquid water really matters because the third one is the, quote, cryosphere, solid form of water such as ice and snow, like the Himalayan glaciers, snow in Ladakh, and polar ice caps.
Exactly. Cryo means cold or ice. Think of like cryogenic freezing.
Right.
The cryosphere gets its own department because frozen water behaves completely differently than liquid water. It's rigid, it's highly reflective, it locks up massive amounts of the Earth's fresh water for thousands of years. So the majestic Himalayan glaciers and the polar ice caps get their own category.
Got it. Next is the, quote, atmosphere, the air surrounding the earth that we breathe, cleaner air in the mountains and forests.
Atmo means vapor or air. This is the invisible ocean of gases we're all swimming at the bottom of.
Just the sky and the wind.
Right. It's the sky, the clouds, the wind, and the very air inflating your lungs right now.
And finally, the fifth department, quote, biosphere, all living organisms and their habitats, including mangroves, forests, farms, ocean plankton, and coral reefs.
Bio is life. If it has DNA, if it grows, reproduces, and dies, it is part of the biosphere.
So, animals, plants.
That includes the towering mangrove forests, the coral reefs, the tigers, the microscopic plankton, and us. We are the biosphere.
Okay, let's unpack this for a second. If I am looking at these 5 spheres, geosphere, hydrosphere, cryosphere, atmosphere, biosphere, it actually reminds me perfectly of the organs in a human body.
Oh, that's an interesting way to look at it.
Think about it. The geosphere is acting like the skeleton, providing the rigid physical structure for everything else to rest on.
Okay, yeah.
The hydrosphere is essentially the circulatory system, this massive network of veins and arteries moving vital fluids around the globe. The atmosphere is obviously the respiratory system, the lungs providing the essential breath of life and regulating temperature.
I see where you're going with this.
Right. And just like in a human body, if the lungs are compromised, if the atmosphere gets sick, the skeleton, the blood, the whole rest of the body suffers. They aren't just sitting next to each other on a shelf. They are functionally reliant on each other to survive.
That is an incredibly sharp analogy. I mean, you cannot treat a patient by only looking at their bones while ignoring their blood pressure. And you can't understand the earth by only looking at the dirt while ignoring the rain. And that perfectly sets up the very next section of the document, where they actually force us to trace these interactions in real time.
Right. The text moves into what I'd call the domino effect of nature. It sets up an exercise. Let me read it.
Go ahead.
We will explore how energy and matter move, interact across the Earth's spheres, and how a change in one affects others. Understanding these processes has been an important part of the continuing journey of the exploration of science.
Setting up the dominoes.
Exactly. It continues. Natural processes, such as heating by solar radiation, movement of air and water, and nutrient cycling, connect these spheres in a delicate balance. Let us understand this by conducting activity 13.1 and explore how different spheres on the Earth continuously interact with each other.
So what's the activity?
It's called Let Us Explore, and it has 4 distinct prompts. Quote, 1. Observe the features of the Earth as shown in Figure 13.1. Identify and circle one example representing each of the geosphere, hydrosphere, cryosphere, atmosphere, and biosphere.
Standard identification.
Yeah. Then, 2. How does snow, cryosphere, eventually become part of the lake, hydrosphere?
Okay, tracking the movement.
Number 3. If there is less snowfall during winters for a few years, how would this affect the lake's level and the grass available for the sheep? And finally, 4. Discuss with your classmates and write down how all the spheres are interconnected and how a disturbance in one can lead to changes in others.
This is essentially a mental detective game. It's asking you to visualize a landscape, say, a high mountain valley, and track a single piece of matter as it moves through the departments.
As a trace it.
Okay, you start with a snowflake falling onto a high mountain peak. Right now, that snowflake is in the cryosphere. It sits there all winter.
Because it's frozen.
Right. But as the Earth tilts and the season changes to spring, the sun's energy hits that snowflake. It melts. The matter transitions from solid to liquid. Now, gravity interacting with the geosphere's steep slopes pulls that water drop down the mountain.
It runs down the rocks.
Yes. It joins a stream and eventually flows into a valley lake. That water drop has now formally transferred into the hydrosphere.
It crossed the border between spheres.
Exactly. But it doesn't stop there. That water in the lake seeps into the soil at the edge of the water, infiltrating the geosphere. The roots of a blade of grass drink that water up, using it to grow.
So now it's in the grass.
Yeah. The water is now inside a living plant, the biosphere.
There.
And then, as the activity suggests, a sheep wanders by and eats the grass. The water, the energy, the nutrients, all of it just transferred into a new part of the biosphere. The activity is forcing you to see the motion. Nothing is static.
But then the activity asks the critical question. What happens if this system is disturbed? What if that snowflake never falls?
Right.
The text actually answers its own question immediately after the activity, and it goes from a tiny local example right up to a planetary crisis.
Let's hear how they explain it.
Quote, from activity 13.1, we can infer that a disturbance in one sphere can lead to changes in others. For example, less snowfall in winters may lead to less water in the lake in summers, resulting in less water to support the growth of grass.
Makes perfect sense.
Similarly, on a large scale, warmer Arabian seawater lead to more evaporation from the sea. This, in turn, causes fluctuations in the southwest monsoon, which results in variability in rainfall, bringing floods to some regions of India while leaving others in drought. This disrupts the hydrosphere.
That's a huge jump in scale.
Right, it gets bigger. At the same time, the rise in atmospheric temperature could eventually accelerate the melting of glaciers and polar ice in the cryosphere, which may lead to the flooding of low-lying regions, and in the long run, it can raise sea levels that may threaten coastal cities. This could disturb the ecosystems within the biosphere by causing a habitat loss.
What's fascinating here is how brilliantly they scale up the domino effect. We start small and logical. Less snow means the lake dries up, which means the grass dies, which means the sheep starves. Simple cause and effect.
Right, very linear.
But then it answers that very first mystery question from the introduction about the Arabian Sea. Let's look at the actual physics of that. The Arabian Sea is a massive body of water, the hydrosphere, the air above it. The atmosphere is getting warmer due to climate change.
Okay.
When air gets hot, it acts like a larger sponge. It has a higher capacity to hold moisture. At the same time, the warm air transfers heat into the top layer of the ocean.
And heat is just energy, right? It makes the water molecules vibrate faster.
Precisely. The water molecules get so energized, they break their liquid bonds and escape into the air as gas. That is evaporation.
So the sponge is filling up.
So now you have a superheated atmosphere holding a massive, unnatural amount of water vapor over the ocean. When the seasonal winds of the Indian monsoon sweep that moisture over the land, the system is fundamentally unbalanced. The engine is misfiring. Instead of a steady, reliable rain over the course of months, the overloaded atmospheric sponge wrings itself out violently. You get catastrophic floods destroying homes in one state because too much water fell too fast, but because all that water dumped in one place, another state gets completely bypassed and suffers a severe drought.
So the atmosphere literally broke the hydrosphere.
And it continues. The text points out that this same heated atmosphere is also acting on the cryosphere. It's melting the polar ice caps and high-altitude glaciers.
Which is bad news.
This isn't just a shame for polar bears. It is a mechanical transfer of mass. Millions of tons of frozen water are turning liquid and pouring into the oceans. The ocean basin acts like a giant bathtub filling up.
And the tub overflows.
The sea level rises and eventually it spills over into human coastal cities. People are forced to abandon their homes. This is what the text means by habitat loss. The physical space where humans and animals live is destroyed by the rising water. It is a stunning cascade of consequences originating from a slight temperature bump in the invisible air.
It really makes you respect the fragility of that delicate balance the text mentioned earlier. You knock over one domino in the atmosphere, and eventually a coastal city floods.
Exactly.
But to understand why the atmosphere is heating up, we have to look at the primary power source we mentioned, the sun. This brings us to section 3 on sunlight and the invisible waves.
Ah, the physics part.
Yeah, the text poses a question. Quote, does the solar radiation heat the Earth's surface evenly? Let us explore how solar radiation varies from the equator to the poles, the oceans to the mountains, and drives many of Earth's natural processes, such as wind, ocean current, water cycle, etc.
Setting up the mechanics.
And then it dives into the physics under the heading 13.1, Uneven Heating of the Earth. It reads, solar radiation is the main source of energy on the Earth. It reaches the Earth as electromagnetic EM waves that travel through a vacuum at the speed of light.
Let me just pause you there for a second. There is some dense, crucial physics vocabulary here that we need to untangle. First, the word vacuum. In normal conversation, a vacuum is the loud machine you clean your rug with.
Right.
In physics, a vacuum is the exact opposite. It is the total eerie silence of absolute empty space. The 93 million miles between the sun and the earth is a vacuum. There is no air, there is no water, there is just nothingness.
Okay, so it travels through nothingness. Then the text has a parenthetical note. It says, unlike EM waves, sound waves, which you studied in Chapter 10, sound waves, characteristics and applications are mechanical waves and require a medium to travel. Why is that comparison important?
Because it explains how the energy actually reaches us. Sound is a mechanical wave. It requires physical stuff to bump into to travel.
Stuff like air?
Yeah, air. When I speak, my vocal cords push air molecules, which bump into other air molecules all the way to your eardrum. If the sun were to explode tomorrow, we wouldn't hear a single sound because there are no air molecules in the vacuum of space to carry the sound waves to Earth.
That's trippy to think about.
It is. But light is an electromagnetic wave. It doesn't need a physical medium. It is pure, self-propagating energy rippling through the emptiness.
And it is unimaginably fast. The text continues. The speed of light in vacuum is 3,808 meters is 1.
That translates to roughly 300,000 kilometers every single second.
Which means the sunlight hitting your face right now actually left the sun about 8 minutes ago.
Exactly. It takes 8 minutes for those waves to cross the vacuum.
Okay, then it gets into the types of waves. Quote, EM waves cover a wide range of frequencies, from high-frequency or short-wavelength radiation, gamma rays and X-rays, to low-frequency or long-wavelength radiation, infrared and radio waves. The high-frequency EM waves, such as gamma rays and X-rays, have very high energy and can be harmful for life on Earth.
Okay, let's tackle frequency and wavelength, because this dictates whether a light wave gives you a tan or gives you radiation poisoning.
Let's do it.
Imagine you and I are holding opposite ends of a long jump rope. If I whip my arm up and down frantically as fast as I can, I'm going to create lots of tight, rapid waves in the rope.
Lots of ripple.
Right. That takes a massive amount of my energy. That is high frequency, short wavelength. In the universe, these are gamma rays and X-rays. They are packed with violent energy. If they hit a living cell, they have enough power to literally shatter the DNA inside it. They are highly harmful to life.
Yeah, the slow ones.
If I just lazily lift my arm up and down, I create long, rolling, slow waves in the jump rope. That takes very little energy. That is low frequency, long wavelength. Things like radio waves, they wash over us all day long, completely harmlessly.
That jump rope visual is fantastic. So the sun is throwing this entire chaotic mix of jump ropes at us constantly. But all of them reach the ground.
Well, let's see what the text says.
The text actually breaks down the exact menu of light we receive. It says, the entire range of electromagnetic radiation, called electromagnetic spectrum, is shown in figure 13.2. However, the solar radiation reaching Earth is concentrated mainly in the ultraviolet, UV, visible and infrared, IR range. About 99% of the sun's energy falls within these wavelengths.
Wow, 99%.
Yeah. These three regions of the spectrum shape the Earth's climate and support life. Gamma rays and X-rays are mostly filtered by the Earth's upper atmosphere, while microwaves and radio waves carry very little energy to significantly warm the Earth.
The electromagnetic spectrum is just science speak for the complete catalog of every type of light wave, from the deadly gamma rays to the harmless radio waves.
Right.
But the text reveals an incredibly lucky break for us. 99% of the solar energy that actually survives the journey and reaches our planet's surface falls into just three very specific categories.
Because the extremes get filtered out.
Yes, the deadly stuff, the X-rays and gamma rays, are physically blocked and absorbed by the outer shields of our atmosphere. We are protected from them. The super weak stuff, the microwaves and radio waves, they do reach us, but they have so little energy they barely affect us. So the entire Earth system, this massive factory, is running almost entirely on just three types of light: ultraviolet, visible light, and infrared.
And the text gives us a precise job description for each of those three light waves. Should I read it?
Please do.
Quote, short wavelength UV radiation is mostly absorbed by the ozone layer in the upper atmosphere, protecting life and contributing to some atmospheric heating.
Worker number one, ultraviolet, or UV.
Right.
It's on the higher energy end. It's dangerous. But thankfully, the Earth has a built-in pair of chemical sunglasses high in the sky called the ozone layer. The ozone absorbs the vast majority of the UV light, taking the hit so our skin doesn't have to. When the ozone absorbs that UV energy, it actually heats up that high layer of the atmosphere.
Then it describes worker number two. Visible light from the sun reaches the Earth's surface and provides energy for photosynthesis, which is the primary source of food for most organisms. It also partly warms the land and water.
This is the absolute MVP of the biosphere.
The visible light.
Right. Visible light passes easily through the atmosphere. It hits a leaf. The plant uses the specific energy of that visible light to literally weld carbon and water together to make sugar. That's photosynthesis. Every single calorie of food you have ever eaten, whether it was a salad or a steak, ultimately contains energy that originated as a visible light wave from the sun.
Wow. Without visible light, the entire food chain collapses instantly.
It's instantly.
And finally, worker number three. The text says, infrared radiation warms the Earth's surface, which then re-radiates this heat back into the atmosphere. A portion of this outgoing heat is trapped by the greenhouse gases, such as carbon dioxide, CO2, methane, CH4, and water vapor, keeping the Earth warm enough to support life.
Worker number three, infrared or IR. You can't see infrared with your eyes, but your skin feels it as heat.
Like when you stand near a fire.
Exactly. When the sun's visible light hits the dark dirt and the deep oceans, they absorb it, warm up, and then they glow with invisible infrared heat, shining that heat back up toward space.
Okay, so it bounces back.
But here is the critical mechanism of our climate. Certain gases in the air, like carbon dioxide and methane, are functionally invisible to incoming visible light, but they are opaque to outgoing infrared heat.
Oh,
They act exactly like a thick wool.
like a wool blanket.
Yes, they trap that returning heat, bouncing it back down to the surface. This is the natural greenhouse effect. If we didn't have it, the infrared heat would just bleed off into the vacuum of space, and the Earth would be a dead, frozen ball of ice.
It is stunning how perfectly calibrated those three waves are for our survival. But the text does drill down a bit more on the dangers and uses of UV light specifically.
Yeah, UV is tricky.
There's a short paragraph that says, the UV rays lie in the wavelength range of 100 millimeter to 400 millimeter, 1 nanometer, 10 to 89 meters, and have a much higher energy than the visible light.
Just to put the math into perspective here, because human brains aren't built to understand a nanometer.
No, 10 to the negative a ninth is hard to picture.
Right. The text says a nanometer is 1/1000th of a meter. To give you a physical sense of that, a single sheet of paper is about 100,000 nanometers thick. A single strand of your DNA is about 2.5 nanometers wide.
That is unimaginably tiny.
So these UV waves are incredibly tight, microscopic ripples of energy.
And the text explains what that energy does. Quote, prolonged exposure to these rays can damage the eyes and skin and increase the risk of cancer. Therefore, people should use UV protective glasses and sunscreen if they are likely to be exposed to UV rays.
And because they are so small and energetic, they can slip right into your skin cells and literally smash the DNA apart. That DNA damage is what a sunburn is, and if it happens too much, the cell mutates and you get skin cancer. That's why sunscreen is a physical necessity.
But the text also points out we've weaponized it for our own good. It says UV rays are also useful in killing germs in water purifiers and help power fluorescent lights.
Exactly. We realized that if UV light is so good at destroying human DNA, it must be great at destroying bacterial DNA too. So engineers put artificial UV light bulbs inside drinking water purifiers.
Oh, that makes total sense.
As the water flows past the bulb, the UV waves blast the bacteria and viruses, shattering their genetic code so they can't reproduce, making the water perfectly safe to drink without using harsh chemicals like chlorine. It's a brilliant hack of physics.
I love when the science connects directly to a kitchen appliance. All right, let's move forward and quantify exactly how much of this solar energy we actually get to play with. This is under a section box labeled Ready to Go Beyond.
Let's hear the numbers.
The text reads, "The amount of the sun's radiation that reaches the Earth's surface is called insolation. It is responsible for warming the Earth's surface and its atmosphere."
Let's extract the vital vocabulary word there, insulation. It sounds exactly like the pink fiberglass insulation in your walls, but it's completely different.
How do you remember it?
An easy way to remember it is to break the word apart. Incoming, SOR radiation, insolation.
Ah, incoming solar radiation. That's clever.
Insolation is just the metric of how much sunlight is striking a given area.
The text then gives us a baseline. It says, the average amount of solar energy received per unit of time, per unit area that is perpendicular to the sun's rays at the top of the Earth's atmosphere is called the solar constant. Its value is approximately 1.4 kilowatts per square meter. 1.4 kilowatt is 2.
Well, let me explain that one too. The solar constant?
Yeah, that's a mouthful.
Imagine you flew up to the very edge of space, right where the atmosphere ends, and you held up a black panel that was exactly 1 meter by 1 meter square. You point it directly at the sun. The amount of raw, unfiltered energy hitting that square is the solar constant. And the text gives us the exact number, 1.4 kilowatts of power.
But obviously, we don't live at the edge of space. We live at the bottom of the atmosphere. How much of that 1.4 kilowatts actually makes it down to us?
Well, the text anticipates that exact question. Let's look at the next part.
It says, the solar constant is important because it helps scientists understand the Earth's energy balance, climate, and weather patterns. However, some of this energy is absorbed and scattered by gases, clouds, and dust particles in the atmosphere before reaching the surface of the Earth.
The atmosphere gets in the way.
Right. As a result, the maximum insolation reaching the Earth's surface is lower than the solar constant, and it's about 1 kilowatt-2 under clear sky conditions.
Okay, so we lose about 0.4 kilowatts on the way down.
Yeah, the atmosphere takes a cut.
Think of the atmosphere as a very dirty, foggy window. As the raw 1.4 kilowatts of sunlight tries to punch through, it hits water vapor, it hits clouds, it hits pollution, it hits dust from the deserts. Some of the light is reflected right back out into space, and some is absorbed by the air itself.
So it's diluted.
By the time it survives the gauntlet and hits the ground on a perfectly clear, cloudless day, it's been diluted down to about 1 kilowatt per square meter.
And the text makes a very specific point about India's geography here. It says, India, due to its geographical location in the tropical and subtropical regions, receives abundant sunlight throughout the year. This makes solar insolation highly significant as it drives the southwest monsoon, which influences India's climate and agriculture.
This is crucial for geopolitics and economics, not just science. Because India sits largely in the tropical and subtropical zones, it is positioned directly under the belly of the sun.
It gets the direct hit.
It doesn't get the glancing, weak sunlight of the higher latitudes. It gets hammered with direct, intense insolation almost 300 days a year. That massive influx of heat energy is the massive physical engine that sucks in the oceanic moisture and powers the southwest monsoon.
And it continues. It also offers immense potential for harnessing solar energy as a renewable and sustainable source of energy.
As the text points out, it is a staggering, untapped reservoir of power. India is essentially being bathed in free, renewable energy every single day.
Which perfectly transitions to the human element of this story. How do we know exactly how much solar energy is hitting India? There's a box here titled Bridging Science and Society that highlights a specific pioneer.
I am so glad they included this.
It reads, Anna Mani, India's pioneering atmospheric scientist, mapped solar insolation across India in the 1950s. Along with S. Rangarajan, she later published Solar Radiation over India in 1982, creating the country's first insolation atlas.
Put yourself in the 1950s. There are no satellites in orbit. There are no digital supercomputers to model the weather.
Right, it was all analog.
If you want to know how much solar energy is hitting the ground, you have to physically go out and measure it. Anna Mani designed and built extremely precise radiation measuring instruments, things like pyranometers, and established a massive network of over 100 stations all across the varied geography of India to track the sunlight day in and day out.
So an installation atlas is basically a map of sunlight.
Exactly. Instead of showing highways and cities, it's a map showing the intensity and duration of solar energy.
And the text finishes with, her pioneering measurements showed India's vast solar energy potential. Today, this is being realized through the large-scale deployment of solar power across the country. India is laying the foundation for a resilient, sustainable, and solar-powered energy future that sets global benchmarks.
Because she did the exhausting foundational field science decades ago, when modern engineers decided to build massive multi-gigawatt solar farms in the 21st century, they didn't have to guess where to put them.
They just looked at her atlas.
They looked at Anna Mani's atlas. She gave them the blueprint for a solar-powered future before solar panels were even commercially viable. It is true scientific foresight.
That is incredible.
Yeah.
To further drive home just how much power we are talking about, the text provides a math problem and a thought experiment. I want to look at both of them.
Math time. Okay.
First, it presents example 13.1. How much solar energy will be received by a 1 meter 2 area in 1 hour if the insolation on the surface of the Earth were 1 kilometers 2?
And the answer?
The answer gives the equation. E, intensity A area ec time. E equals 1 A1000, JAS 1 meters to 2 down 1 meters 2, Danes 38600s. E equals 3.6, cans 1060A.
Okay, the math can look intimidating with all the joules and scientific notation, but let's just focus on the real-world translation the text provides.
Good, because the text actually gives us one. It says in parentheses, this amount of energy is approximately equal to the energy needed to melt 5 kilograms of ice and heat the water obtained to 100 degrees C. It is also equal to 1 unit of electricity used in a household, as shown on an electricity bill.
That's the translation we need. Imagine a patch of ground the size of a small dining room table, 1 square meter. Let the midday sun shine on it for exactly 1 hour.
Just 1 hour.
The raw energy that falls silently onto that small patch of dirt is enough to take 5 kilograms. That's 11 pounds of solid, freezing ice, melt it completely into water, and then boil that water until it vaporizes. That is a staggering amount of thermal energy.
When you scale that up to the size of a country, the mind kind of boggles, which makes that next part, the Thar Desert thought experiment, so powerful.
Read that one.
Think as a scientist. An interesting estimation problem that helps us to appreciate the enormous amount of energy that we get from the sun is to estimate how much of the Earth's surface would be needed to be covered with solar panels to supply all the electric power that our country uses today.
It really is the ultimate perspective shift.
It finishes with, you will probably find that even a fraction of the area of the Thar Desert, if covered with solar panels, could supply India's electricity needs.
The Thar Desert is vast, sun-baked, and largely uninhabitable. The text is asking you to realize that if you took just a tiny fraction of that barren wasteland and carpeted it with modern solar panels to capture that incoming 1 kilowatt per square meter, you could generate enough electricity to run every light bulb, every air conditioner, every factory, and every train in the entire nation of India.
It's a fraction of a desert.
We are not suffering from a lack of energy on this planet. We are bathed in an infinite abundance of it. We just have to build the tools to catch it.
But catching that energy depends heavily on what kind of surface the sunlight hits. This brings us to a crucial concept in Section 5 about how the Earth actually interacts with the light.
Right, albedo.
Exactly. The text reads, the fraction of solar radiation reflected by a surface is called its albedo. The word albedo comes from Latin, which means whiteness. High albedo surfaces stay cool because they reflect more light, while low albedo ones heat up more quickly as they reflect less and absorb more light.
Albedo is one of those scientific terms that sounds complex, but it's a concept you already understand instinctively. The text notes it comes from the Latin word for whiteness.
It's like wearing a black shirt on a sunny day.
Exactly. Think about walking barefoot on a hot summer day. If you step on black asphalt, it burns your feet. If you step on a white concrete sidewalk, it's significantly cooler. Why? Because the black asphalt has a very low albedo. It acts like a dark sponge, absorbing almost all the visible light energy and converting it into baking heat.
And the white concrete.
The white concrete has a high albedo. It acts like a mirror, reflecting the light away before it can turn into heat.
And the text gives us a table to show the extreme planetary examples of this. Table 13.1. Reflection of solar radiation by surfaces of materials. It gives the albedo values for a few materials. 1. Snow, 0.80 to 0.90. 2. Ice, 0.50 to 0.70. 3. Crushed rock, 0.250 to 0.30.
Right. The table says snow has an albedo of 0.80 to 0.90. The scale goes from 0 to 1, so 0.90 means pure. Fresh snow is reflecting 90% of the sun's energy straight back into space like a giant blinding mirror.
Wow, 90%.
This is why you can get sunburn under your chin when you go skiing. The light is bouncing off the ground. And it explains why the North and South poles stay freezing cold even during the summer when the sun is shining on them 24 hours a day. The heat literally bounces off.
But then the text concludes. From Table 13.1, you must have seen that snow and ice have high albedo, meaning they reflect a large proportion of the incoming solar radiation. This makes polar regions very cold. On the other hand, surfaces like black soil and ocean water have lower albedo as they absorb more solar radiation, and hence they are relatively warmer.
And look at what happens when things change. Let's say the atmosphere warms up just a little bit and some of that high albedo sea ice melts. What's underneath the ice? The dark, deep ocean water.
Which has a low albedo.
Right. The ocean has a very low albedo. It absorbs heat greedily. So the dark ocean absorbs the heat, which warms the water, which melts more ice, which exposes more dark ocean, which absorbs more heat.
It's a runaway train.
It is a terrifying, self-reinforcing feedback loop. It's called the ice albedo feedback, and it's one of the main reasons the Arctic is currently heating up nearly 4 times faster than the rest of the planet.
So the surface absorbs the heat. But what happens to it then? It doesn't just disappear. The text covers this next. It reads, "You have also learned in the earlier grades that all objects radiate heat."
Energy can't just vanish.
Right. It continues. "We feel hot inside a concrete house at night, especially during hot summer. This is due to the heat re-radiated by the concrete during the night. However, traditional houses built with thick mud and wooden walls offer cool conditions even in hot summer due to less re-radiation."
This is the second half of the albedo story. Re-radiation. Energy cannot be destroyed. It can only change form. If a low albedo surface absorbs a ton of visible light all day, it stores it as thermal energy. But eventually it has to get it back.
And concrete is good at storing it.
Modern concrete is incredibly dense. It soaks up heat all day long. When the sun goes down and the air cools off, the concrete begins to slowly release or re-radiate that stored heat in the form of infrared energy. That's why a modern concrete apartment can feel like a stifling oven at 11:00 p.m. long after the sun has set. The building itself is glowing with invisible heat.
And the text contrasts that with traditional architecture.
Exactly. Traditional mud and wood houses have different thermal properties. They might have a different albedo, but more importantly, they don't store heat in the same dense, massive way that concrete does. So when the sun goes down, they don't have this massive reservoir of heat to re-radiate into the living space, keeping the interior naturally cooler.
It's a fascinating look at how human choices in the geosphere, our building materials, interact with solar insolation to dictate our comfort.
Yeah.
The next part of the text scales back up to the planetary level to explain the biggest temperature difference on Earth. It is under the heading 13.1.2 Latitude and Earth's Shape.
Let's zoom back out.
Quote, "You have already learned in earlier grades that the Earth is spherical. As a result, the sun's rays strike different latitudes at different angles on the Earth. The sun's radiation falling on the equatorial region is concentrated over a smaller area, where it is spread over a larger area in the polar region."
To really grasp this, we need a mental model. Imagine you are in a dark room holding a very powerful, perfectly round flashlight.
Okay, I have a flashlight.
You shine it directly at the middle of a basketball. That circle of light on the equator of the ball is tight, bright, and highly concentrated. That represents intense insolation, lots of watts per square meter.
Right.
Now, without moving the flashlight, imagine looking at where the beam hits the top curve of the basketball, near the pole. Because the surface curves away, that exact same beam of light gets smeared and stretched out into a long, dim oval.
Ah.
You have the exact same amount of energy, but it's now spread over a much larger surface area, so the intensity is drastically diluted.
The text actually says exactly that. This is why equatorial regions remain relatively warm throughout the year, whereas polar regions experience much colder conditions. This uneven heating creates temperature differences between the equator and the poles.
So simply because the Earth is round, the equator is constantly baking under the concentrated flashlight, while the poles are shivering under the smeared out light.
And it mentions the tilt too. You've also learned how the Earth's spherical shape and the tilt of the Earth's axis of rotation give rise to seasons and the changing length of daytime during one revolution of the Earth around the sun.
Right, which shifts the heat around over the year.
But the main point is the conclusion. Thus, solar radiation is not evenly distributed across the globe. This uneven heating of the Earth's surface across the globe drives global winds and ocean currents.
This creates a massive planetary problem. The equator is building up an immense surplus of heat, while the poles are running a massive heat deficit. But nature abhors a vacuum, and it hates an imbalance.
It wants to equalize.
The Earth is constantly trying to equalize its temperature. The entire purpose of the atmosphere and the hydrosphere is to act as a planetary HVAC system, desperately trying to drag that excess heat from the equator and dump it at the freezing poles. That struggle to balance the ledger is what creates every gust of wind, every hurricane, and every massive ocean current on the planet.
That is a brilliant way to frame the weather. Let's look exactly at how the atmosphere manages that job. The text moves into 13.1.3 role of the atmosphere. It reads, "The air surrounding the Earth is called atmosphere. It is held in place by the force of Earth's gravity. It consists mainly of nitrogen, 78%, and oxygen, 21%, along with small amounts of argon, carbon dioxide, water vapor, and other gases."
First off, it's a great reminder that the air isn't nothing. It is a physical fluid, a heavy soup made mostly of nitrogen, which doesn't do much for us, and oxygen, which keeps us alive.
It's heavy, right?
Yeah, and the only reason it doesn't just float away into the vacuum of space is because the Earth's gravity is pulling it down, pinning it to the rock. But the really interesting part is the layer cake structure of it.
The text provides Table 13.2, key atmospheric layers. It lists two main ones for our purposes. Troposphere, 0 to 12 kilometers. Weather formation, temperature decreases with height. And the stratosphere, 1250 kilometers. Ozone layer absorbs UV, temperature increases with height.
The bottom layer, from the dirt up to about 12 kilometers high, is the troposphere. This is our domain. Every human being who has ever lived, every cloud, every thunderstorm, and every commercial jet flight exists inside the troposphere. And as anyone who has climbed a mountain knows, in the troposphere, the higher you go, the colder it gets.
But then you cross an invisible border into the stratosphere, and the rules completely flip. The text explains it. In the stratosphere, 12 to 50 kilometers, where the ozone layer is located, ozone absorbs UV rays and heats up the atmosphere, so temperature rises with height.
Yes, and this is wild. Between 12 and 50 kilometers up, the temperature actually starts getting hotter the higher you climb. Why? Because the ozone layer lives up there.
Absorbing the UV rays like you mentioned earlier.
Exactly. The ozone is absorbing that brutal, high-energy UV radiation from the sun, and that friction generates heat. Now think about hot air balloons. Hot air naturally wants to rise, while cold air sinks. Because the top of the stratosphere is artificially heated by the ozone, the hot air is already at the top. There is no reason for the air to churn or mix vertically. It is incredibly stable and calm.
Oh, that makes sense. And the text notes that this increase in temperature with height in the stratosphere calms the layer due to the lack of vertical mixing of air, keeping weather confined to the troposphere.
Because it's so heavy and stable, it acts like a giant invisible lid sitting on top of the boiling pot of the troposphere, trapping all the chaotic, stormy weather down where we live.
The text then summarizes the entire dual purpose of the atmosphere in a single, powerful paragraph. It reads, "The atmosphere plays two crucial roles in protecting the life on the Earth. Firstly, it partly absorbs the incoming solar radiation. The ozone layer blocks the harmful UV rays. Clouds and other gases also absorb some sunlight before it reaches the surface of the Earth.
That's role number one.
Then, secondly, it traps outgoing heat. The Earth's surface absorbs sunlight and re-radiates it in the infrared region. Greenhouse gases like CO2, CH4, and water vapor absorb this re-radiated heat, preventing it from escaping into space. Without the atmosphere, the Earth would be too cold for life to survive."
I love reducing complex systems to their simplest metaphors. The atmosphere is our shield, and it is our blanket.
Shield and blanket.
The stratosphere and the ozone layer act as the shield, taking the brutal hit from the solar UV radiation so our DNA doesn't fry. Down in the troposphere, the greenhouse gases act as the blanket, catching the infrared body heat the Earth is radiating and holding it close so we don't freeze to death in the cold of space. It's a miraculous balance.
But the text ends with a truly terrifying cautionary tale. Venus, it says. However, excess CO2 from human activities enhances the greenhouse effect, causing global warming, which, if left unchecked, could make the Earth uninhabitable. You have also learned that Venus is hotter than Mercury, even though Mercury is closer to the Sun. This is because of the presence of an atmosphere on Venus, which has led to an uncontrolled greenhouse effect.
Logic would tell you that Mercury should be the hottest planet because it's physically closest to the fire of the sun.
Yeah, that seems obvious.
Mercury is scorched. But Venus is actually much, much hotter. The surface of Venus is around 900 degrees Fahrenheit, hot enough to melt solid lead. And the reason is entirely atmospheric.
It's all because of the greenhouse effect.
Venus has a monstrously thick atmosphere made almost entirely of carbon dioxide. It is the ultimate runaway greenhouse effect. The thick CO2 blanket let the sun's heat in, but refused to let any of the infrared heat out. The heat just built up and built up until the entire planet baked into a sterile hellscape.
That is a chilling comparison, no pun intended. The text is very explicitly warning us.
The physics of the greenhouse effect are non-negotiable. If we keep pumping excess CO2 into our own atmosphere, we are thickening our blanket, and we are risking pushing our perfect Goldilocks planet toward an unlivable extreme.
Speaking of studying the atmosphere, there's another fascinating historical box here about how we actually learn this stuff. It reads, K.R. Ramanathan, India's atmospheric scientist, climbed to an altitude of 18,000 feet in the Himalayas in 1934 to measure the ozone levels and discovered that they were lower than expected.
1934.
His work laid the foundation for understanding how UV absorption varies with altitude and pollution. Later on, he led early monsoon forecasting efforts.
This is a testament to the raw physical grit of early scientists. In 1934, we didn't have weather satellites. We couldn't just log into a computer to check the ozone thickness.
You had to walk up there.
If you wanted to know what was happening in the upper atmosphere, you had to physically go there. Ramanathan had to haul heavy, delicate, brass and glass scientific instruments 18,000 feet up into the freezing, oxygen-deprived death zone of the Himalayas just to get a clear measurement. It reminds us that mapping these invisible layers of protection wasn't just a theoretical math exercise. It required immense physical exploration and risk.
It's astonishing dedication. Now, the text shifts our focus from the swirling air above us to the swirling water below us. Let's look at ocean currents. The text reads, Ocean currents play a major role in regulating the Earth's climate and supporting life. By transporting heat from the equator towards the poles, they reduce temperature differences across the planet.
So we'll go back to our flashlight on the basketball analogy.
Right, moving the heat around.
The equator has too much heat, the poles have too little. The wind tries to balance it, but air can only carry so much heat. Water, however, has a massive thermal capacity. It can hold onto heat for a very long time. Ocean currents are nature's giant underwater conveyor belts.
And the text gives a great example. Quote, For example, the warm ocean current, the North Atlantic Drift, an extension of the Gulf Stream, a strong ocean current carrying warm water from the southern part of the North American East Coast across the Atlantic Ocean, flows toward the northwestern coast of Europe and keeps many ports ice-free during winter, even at high latitudes.
The Gulf Stream is a perfect example. The ocean near the equator in the Atlantic absorbs massive amounts of solar insolation. The water gets hot. That huge river of hot water sweeps up the coast of Florida and then shoots diagonally all the way across the Atlantic Ocean, aiming right at Europe.
And without that, Europe would look very different. The text adds, This moderating influence on climate also supports human activities, such as trade and commerce. Ocean currents also support a massive ecosystem by transporting nutrients.
Look at a globe sometime. Countries like the United Kingdom and Norway are incredibly far north. They're at the same latitude as parts of Canada that are frozen tundra. By all rights, Europe should be buried in ice all winter. But because this massive invisible river of warm tropical water is constantly flowing past their shores, it acts like a continent-sized radiator. It warms the air blowing over Europe, keeping their climate temperate and keeping their seaports completely free of ice even in January.
There's a quick pause and ponder question here that highlights exactly that. 3. What happens to the warm surface of water from the equator as it travels toward the poles? What impact does this movement have on the area?
The movement of that water literally makes entire regions of the Earth habitable for human civilization.
And to understand a system that massive, you need massive tools. The text highlights this in a box called India's Scientific Contributions.
What tools are they using?
It reads, Scientists at the Indian Institute of Tropical Meteorology, IITM, Pune, run advanced computer models that couple the energy flows we discussed in this chapter between atmosphere, oceans, land, and ice to simulate the Indian monsoon.
Those are supercomputers?
Yeah. These models use data from satellites, buoys in the Indian Ocean, and even stations in Antarctica to improve seasonal forecasts and to study how global warming may change monsoon rainfall patterns across India.
This really brings the whole Earth as a system concept full circle. The scientists at IITM in Pune aren't just looking out the window at the clouds to predict the monsoon.
Because it's all connected.
Because the Earth is one tangled web, you can't predict the rain over a farm in Punjab without knowing what the ocean is doing. To build an accurate computer model, they have to feed their supercomputers data from satellites orbiting in space, from robotic buoys bobbing in the middle of the Indian Ocean, and incredibly, from weather stations sitting on the ice of Antarctica.
Wait, Antarctica?
Yeah. The temperature of the ice at the bottom of the world mathematically influences the rainfall at the equator. You cannot understand local weather without understanding the global machine.
That is just mind-blowing scale. Okay, we are moving into section 7, which introduces a massive new concept about how the materials of the Earth actually circulate. The text introduces it under the heading 13.3 Biogeochemical Cycles.
Ah, the big word.
Let me read it. Living organisms constantly exchange matter and energy with the air, water, soil, and rocks around them. This continuous interaction between the non-living abiotic and living biotic components of the Earth results in the transfer of matter and energy across various spheres of the Earth, as discussed earlier.
Let's just chop up that intimidating $10 word really quick. Biogeochemical.
Break it down for us.
Bio means living things. The trees, the animals, the bacteria. Geo means the earth, the rocks, the soil, the water, the air. And chemical refers to the literal atoms and molecules, the raw matter itself. So a biogeochemical cycle is simply the roadmap that a single atom takes as it travels endlessly through the system.
And the text says this recycling is essential. This process ensures that essential nutrients, such as carbon, nitrogen, and oxygen, are recycled and remain available to support life on the Earth. The cyclic movement of matter and energy between the abiotic and biotic components is called the biogeochemical cycle.
Here's the most profound realization. The Earth is essentially a spaceship. It's a closed system.
Meaning we don't get new stuff.
Right. We do not get new shipments of carbon or water from outer space. The glass of water you drank this morning is the exact same water that a dinosaur drank 65 million years ago. The planet is the ultimate, inescapable recycling facility. It constantly shuffles these vital atoms between the biotic, living, and abiotic dead parts of the world, so we never ever run out of the building blocks of life.
Let's look at the first cycle they detail, the water cycle. 13.3.1 water cycle. You've studied the water cycle and learnt terms like evaporation, transpiration, condensation, precipitation, infiltration, and groundwater.
The classic second grade science lesson. Exactly. In this cycle, water evaporates from water bodies, such as rivers, lakes, oceans, etc., and condenses to form clouds. It returns as precipitation in the form of rain, hail, or snow to the surface, and finally flows back to the ocean.
Water evaporates, forms fluffy clouds, falls as gentle rain, flows into the river. We know that one.
Some of the water seeps through soil and rocks beneath the Earth's surface. Water dissolves minerals from soil and rocks. It also supports all terrestrial organisms and transports these nutrients to oceans and support marine life. But then, the text hits us with a critical paragraph on how we are breaking this cycle today.
Things are changing.
It reads, climate change is now affecting the water cycle. For example, a warmer atmosphere holds more moisture, causing heavier rains in some areas, like intensified monsoons and droughts elsewhere.
As we noted earlier, a hotter atmosphere acts like a bigger sponge, holding more water vapor. When that overloaded sponge finally reaches its limit, you don't get a gentle, soaking rain, you get an apocalyptic deluge. And the text explains the consequences of that. Melting glaciers add more water to rivers, raising sea levels in the long run and threatening coastal cities, such as Mumbai and Chennai. Sudden bursts of intense rainfall result in more runoff that erodes soil, and less infiltration reduces the recharge of groundwater, which in turn makes sustaining agriculture difficult, especially during dry months.
And here's where the mechanics really matter. When rain falls that hard and that fast, it cannot gently soak or infiltrate into the soil to refill the deep underground aquifers that farmers rely on for irrigation.
It just washes away.
Instead, the water hits the dirt and violently bounces off, creating runoff. It acts like a liquid bulldozer, scraping the nutrient-rich topsoil away and dumping it into the ocean. So in a cruel irony, because the storms are too intense, the water runs away instead of soaking in, meaning our underground wells are drying up even as the surface floods.
The summary here is brutal. In this way, the water cycle links the cryosphere, glaciers, hydrosphere, rivers and oceans, atmosphere, moisture, geosphere, soil erosion and decreased infiltration, and biosphere, crops and fisheries, all of which are affected by global warming.
You are seeing the atmosphere heat up, which weaponizes the hydrosphere into floods, which scours the geosphere of its soil, which starves the biosphere of crops.
It is a brutal chain reaction, but the next cycle is arguably the most critical for understanding why the climate is changing in the first place. Let's look at the carbon cycle.
This is the big one.
The text reads 13.3.2 carbon cycle. Carbon forms the backbone of life. Every protein, carbohydrate, fat, and DNA molecule contains carbon.
We are made of carbon.
It circulates continuously between the atmosphere, CO2 gas, biosphere, plants and animals, geosphere, carbonate rocks and fossil fuels, such as coal and oil, and the hydrosphere, dissolved CO2 in marine shells. Different parts of the carbon cycle operate at very different timescales.
Pay close attention to that part about the timescales.
Quote, in the fast cycle, which happens over days to years, plants convert atmospheric CO2 into glucose using sunlight through photosynthesis. CO2 is released back into the atmosphere through respiration. Animals eat plants and/or other animals. When they die, CO2 returns to air because of decomposition.
The text brilliantly solves the confusion around carbon by dividing the cycle into two distinct gears, the fast cycle and the slow cycle. The fast cycle is happening literally right now inside your lungs. You take a breath, your cells burn energy, and you exhale carbon dioxide. That's respiration.
Right.
The oak tree outside your window pulls that CO2 out of the air, uses sunlight to break it apart, and builds a leaf. A caterpillar eats the leaf. A bird eats the caterpillar. The bird dies, bacteria rot the bird, and the carbon goes back into the air. That carbon is moving fast, cycling through the biosphere and atmosphere over days, months, or a few years. It's a balanced, rapid loop.
But the text then introduces the other gear. In the slow cycle, which happens over millions of years, dead plants and animals get buried and are converted to fossil fuels, such as coal, oil, and gas.
The slow cycle is a completely different beast. Let's trace it. Hundreds of millions of years ago, before dinosaurs even existed, massive swamps of giant ferns died. They fell into the muck where there was no oxygen, so they couldn't rot. They just piled up.
And got buried.
Over millions of years, they were buried under thousands of feet of mud and rock. The immense crushing pressure and geothermal heat of the geosphere cooked those dead plants, slowly compressing their carbon into solid rock coal or thick liquid oil.
So it's basically trapped down there.
The Earth had essentially taken trillions of tons of carbon out of the active atmosphere and locked it away deep in the basement vault of the geosphere. It was out of circulation.
But the text points out what we do with it. These fuels are burnt to provide energy for various needs like heating, cooking, transportation, and industrial purposes. When fossil fuels are burnt, carbon is released back as CO2 on a very short time scale.
And that?
Wait, if I'm putting this together. When we build an oil rig or a coal mine, we are digging into that vault. When we burn that coal in a power plant to run our air conditioners, what we are essentially doing is taking millions of years worth of slow cycle carbon that the Earth had safely buried, and we are violently dumping it all back into the fast cycle atmosphere in the span of just a few decades.
You have hit the exact mechanical root of the climate crisis. The time disparity is the entire problem. It took the Earth 300 million years to slowly bury that carbon. Humanity dug it up and lit it on fire in about 200 years. We are unleashing a tidal wave of ancient carbon into an atmosphere that is simply not equipped to handle that volume.
That sudden massive influx of CO2 is what is rapidly thickening the greenhouse blanket, trapping the infrared heat and driving global warming.
You cannot merge the slow cycle into the fast cycle without blowing up the engine.
Wow. When you frame it as a collision of timelines, it makes terrifying sense.
It does.
The text then moves into Section 8, exploring another critical cycle before looking at the broader human impact. Let's look at the oxygen cycle.
Let's balance the ledger.
Quote, metal oxides and minerals, and in the air is carbon dioxide. While discussing the oxygen cycle, we focus on processes that regulate the oxygen level in the atmosphere. Organisms like plants and animals use oxygen for respiration and releases CO2. Combustion of fuels uses oxygen and releases CO2.
That's the consumption side. Every animal on Earth breathing and every fire burning is taking free oxygen out of the air and binding it to carbon to make CO2.
And the production side. Plants restore oxygen through photosynthesis using sunlight, water, and CO2 to form glucose and release O2.
On the credit side, you have production. The trees, and critically the massive blooms of microscopic ocean plankton we talked about earlier, are taking that CO2, keeping the carbon to build their bodies, and spitting the pure oxygen back out as a waste product.
And it summarizes it. This balance between consumption, respiration, and combustion and production, photosynthesis, circulates oxygen between the atmosphere, land, oceans, and living organisms, sustaining life across all spheres of the Earth.
As long as the amount of oxygen being consumed roughly matches the amount being produced by photosynthesis, the atmospheric ledger is balanced and complex life can thrive.
But, as the text immediately points out, humanity is cooking the books. Let's read the section on our specific impact.
Okay, brace yourself.
13.4 Human Impact on Earth's Processes. You have learned about the impact of climate change earlier, in which we examined the crises our planet Earth is facing. Rising CO2 levels from the use of fossil fuels leads to extreme weather and biodiversity loss.
Okay, so that's the carbon cycle disruption.
Right. Then it says, excess atmospheric CO2 increases ocean absorption, making seawater more acidic. This could threaten tiny plankton and coral reefs, disrupting the marine ecosystems.
This paragraph is a masterclass in translating abstract science into tangible devastation. First, the CO2 in the oceans. The ocean acts as a massive carbon sink. It absorbs about a quarter of the CO2 we pump into the air. But when you force too much CO2 into salt water, it undergoes a chemical reaction that creates carbonic acid.
The ocean is literally becoming more acidic.
And here's the tragedy. Coral reefs and tiny plankton build their delicate shells out of calcium carbonate. In acidic water, those shells literally dissolve while the creature is still inside them. By altering the atmosphere, we are melting the foundation of the marine biosphere.
And the second disruption focuses on agriculture. Quote, the overuse of fertilizers in agriculture adds excessive nitrogen via nitrates to rivers and lakes, causing widespread growth of algae, algal blooms, that deplete oxygen and kill fish. This process is called eutrophication, which threatens water bodies and coastal fisheries.
Eutrophication. This is what happens when we disrupt the nitrogen cycle. To grow massive amounts of food, humans use synthetic nitrogen fertilizers, but crops don't absorb all of it. When it rains, the excess nitrogen washes off the dirt into lakes and rivers.
And nitrogen is plant food.
Exactly. So when it hits the lake, the microscopic algae in the water gorge on it and explode in an unnatural, massive algal bloom. The lake turns thick, slimy green, blocking the sunlight.
But then it dies.
Algae lives fast and dies fast. When that massive green mat dies, millions of bacteria show up to eat the rotting algae. Those bacteria breathe oxygen. They consume so much oxygen during the rotting process that they suck the water completely dry of it. The lake becomes a dead zone, and millions of fish literally suffocate to death underwater. Eutrophication is the cascade of death caused by too much nutrient.
It's horrifying. And the third disruption is deforestation, which we touched on in the very first mystery question.
The domino effect.
Quote, deforestation also creates multiple effects across air, water, land, and living organisms. Clearing forests results in decreased photosynthesis and reduced transpiration, which can lead to decline in the local rainfall.
Deforestation proves how interconnected the spheres are. You pull one thread and the whole tapestry unravels. You are removing the leaves that sweat moisture into the air transpiration, which literally stops the local rain clouds from forming, crippling the hydrosphere.
And then it also alters surface albedo. Without tree roots to hold the soil together, soil erosion could increase. Over time, habitats could be destroyed, leading to a decline in biodiversity as many species lose their natural homes.
Right. You aren't just killing trees. You are removing the physical roots that grip the geosphere, leading to massive mudslides and soil erosion. And you are changing the albedo of the land, making it absorb more heat.
But the text refuses to leave us in a state of despair. It immediately pivots to how we can fix the engine.
Thank goodness.
It reads, while human impact affects all Earth's spheres, a combination of local actions and global cooperation can help restore the Earth's natural systems. For example, the Montreal Protocol has started the process of recovery of the ozone layer through global cooperation.
This section forces us to ask a very hard question. Is it actually possible for humanity to coordinate and fix a planetary problem? And the text points to the Montreal Protocol as definitive proof that we can.
That was for the ozone layer, right?
Back in the 1980s, scientists realized that CFCs, chemicals used in every hairspray can and refrigerator on Earth, were literally ripping a hole in the stratospheric ozone layer. We were destroying our UV shield. But humanity actually listened to the science. Every nation on Earth came together, signed the Montreal Protocol, and banned those chemicals. And today, the ozone hole is actively shrinking and healing. It is the greatest environmental success story in history.
But the text is brutally honest that things like the Paris Agreement haven't worked as well.
Mhm.
However, the Kyoto Protocol and the Paris Agreement, in which countries were supposed to reduce their CO2 emissions, have been less successful.
Because banning hairspray is economically easy.
Yeah.
Transitioning the entire global economy away from the slow carbon cycle fossil fuels is incredibly hard.
But the text highlights tangible, massive actions happening right now. Conserving energy and energy resources, switching to renewable energy resources like solar and wind, planting trees, saving water, and practicing sustainable farming can help restore the balance. India has planted billions of trees, expanded energy from solar and renewable sources significantly, and also promoted sustainable farming practices.
It shows that the solution isn't just one magic bullet, it's a combination of massive geopolitical shifts and local physical restoration. India planting billions of trees to act as natural carbon vacuums, pulling CO2 out of the air. The massive expansion of those solar farms we talked about earlier, tapping into the free insulation.
And the text brings those solutions down to the individual level. It summarizes the chapter in the at-a-glance bullet points,
Mm-hmm.
and it ends with a final paragraph about mission life. Let me read that.
These do.
Mission life to lifestyle for environment. An India-led global initiative introduced at the United Nations Climate Change Conference in 2021 encourages people to adopt mindful, eco-friendly lifestyles. Traditional practices and ancient texts in India have long recognized that the Earth functions as an interconnected system. The Earth works through the flow of energy and the cycling of matter across spheres.
It's the perfect philosophical capstone to all this intense science. When you spend an hour learning about the unfathomable power of the sun, the crushing weight of the oceans, and the millions of years of the slow carbon cycle, an individual human can feel incredibly small and powerless. What can one person do to fix the atmosphere?
Well, the text answers that. Unsustainable consumption disturbs this balance. By promoting simple habits, such as saving energy and conserving resources, Mission Life highlights how the actions of individuals and communities can help build a sustainable future.
Mission life reminds us of the core lesson of the text. Literally everything is connected. Because the spheres are intertwined, small mindful habits by a single individual create ripples. If you choose to walk instead of drive, you burn less fuel. That demands less oil from the geosphere. That emits less CO2 into the fast cycle. That leaves the atmospheric blanket a little bit thinner. That absorbs a little less heat. That melts a little less ice in the cryosphere.
Your individual lifestyle choices are physically wired into the massive Earth system.
Exactly.
I love how actionable that makes it feel. Now, there is one final brilliant exercise right at the end of the chapter that forces you to realize just how connected you are.
Oh, the meal experiment. I love this.
Yeah, the text poses this challenge. Quote, choose any one meal you ate recently. It could be anything. For example, roti and dal, rice and sambar, idli and chutney, and so on. For each main item in the meal, find out and explain how the carbon in it originally came from carbon dioxide in the air through photosynthesis, and two, how the nitrogen in it likely came from the atmosphere into the soil, for example, by bacteria, or through the Haber-Bosch process in fertilizers, and then into the plant.
I implore everyone listening to actually sit down tonight and try this mental exercise with whatever is on your plate. It is a profound meditation. Let's trace a simple meal of roti and dal. Look at the roti. The solid starch in that wheat is made almost entirely of carbon atom.
Where do the solid atoms come from?
They weren't pulled up from the dirt. The wheat plant opened microscopic pores in its leaves and literally inhaled invisible carbon dioxide gas from the sky. It used the visible light wave from the sun to rip the carbon atom away from the oxygen and wove that atmospheric carbon into the solid food you were chewing. You were quite literally eating the sky.
And what about the nitrogen in the dal?
The lentil plant that made the dal needs nitrogen to build the protein you need to build your muscles. The atmosphere is 78% nitrogen gas, but it's useless to plants. They can't breathe it. But down in the geosphere, microscopic bacteria living on the roots of the lentil plant fix that nitrogen. They pull the gas from the air trapped in the soil, run a chemical reaction, and turn it into a solid fertilizer the plant can drink up.
So it comes from the air into the soil, into the plant, into you.
When you eat the dal, the nitrogen that was floating over the farm a few months ago becomes the nitrogen physically building the muscle in your arm. When you trace your meal atom by atom, you realize you aren't just an observer living on the earth. You are an active participant in the biogeochemical cycles. You are made of the spheres.
That is an incredibly beautiful, unifying way to look at a simple plate of food. We have covered a staggering amount of ground today in this deep dive.
We really did.
We've traced the sun's rays through the vacuum of space. We followed a melting snowflake down a mountain. We tracked a carbon atom through millions of years of history. And we've seen how the choices we make today dictate the future of the planet's operating system.
It is a machine of breathtaking complexity, and it has been a genuine pleasure to break it down. And to leave you with one final thought, I want to point to a tiny text block at the very end of the document titled, "The Quest Continues." It says, quote, "New tools are allowing scientists to observe the planet in real time. What new discoveries will these tools reveal?"
The science isn't done.
The science in this document isn't finished, it's just the baseline. As you look at the sky or the dirt today, ask yourself, what invisible connections, what flowing energy and matter are happening right in front of you right now that we haven't even invented the tools to see yet?
The machine is endlessly complex, and the engine is still running. Until next time, keep looking deeper.